Good morning, everyone. Welcome to the webinar on solar-powered water systems in humanitarian context, specific considerations and limitations of solar-powered water system. My name is Ranisha Basnith, and today I'll be your moderator for this webinar, and I'm joined in by my colleague Alberto, who will be helping me during the Q&A session during the webinar. As you know, this webinar is organized jointly by the Solar Hub, IOM, Oxfam, USAID, and Energypedia, and is part of an ongoing webinar series. And it is a 4-part webinar series where we organized 2 webinars in November 2020 and Jan 2021, where we discussed the basics like what are the different types of solar pumping, how do you solarize existing systems, and so on. So in case you have not attended any of our previous webinar, my colleague is going to drop a link in the chat box or the question box where you can then access the link and have a look at our previous webinar recordings as well as download the presentations. We will record the webinar from that is organized today and also provide you with all the presentations after the webinar. So please do stay tuned for the recordings and for the links that will be sent to you after the webinar in a follow-up email. And we also have one more webinar coming up to us the end of March, where we were talking about how to make the system, solar-powered water system, more sustainable. So do stay tuned for that. And in today's webinar, after the webinar, you have an option to fill out a survey where you can actually leave your email address so that we can send you an invite to the other webinars after this webinar. So please have a look out for those one too. So let's kickstart the webinar with a few of house rules. So today we will be taking all of your questions. And if you have attended our previous webinar, you know that we answer all the questions that you send in. So we try to answer as much as possible during the live webinar. And whatever questions we cannot answer, we always document in the documentation page, which you again have access in a follow-up email. So please use the question box to send us as many of your questions as possible. So on the right side of your screen, you should have a control panel, and there you should have a window called as question. And you can just type your question and send it to us. In case you are using any Android device or an iPad, then when you open the webinar, on the top right corner, there is something like a question mark. And when you click on that, then a pop-up will appear where you can type in your questions. So please use these options to send in your questions. So now let's have a quick look at today's agenda. Today we'll kickstart with an introduction presentation from Engineers Without Border. Then we will dive deeper with a case study from Bangladesh from Oxfam. And finally, we have a third presentation from IOM where we will look at the practical consideration for planning SPWS systems in humanitarian context. So without further ado, I would like to invite our first presenter for today, Jared Hostetler from Engineers Without Borders, USA. Jared is a senior principal engineer with Hazen and Saver and has been an Engineer Without Border USA volunteer since 2019. And today he's going to quickly introduce the topic about what are the practical considerations for planning SPWS system. So since Jared is based in USA and because of the time difference, it is too early for him, we have a recorded presentation which I'm going to place shortly. So please allow a few seconds for the presentation to load and be displayed on your screen. And if you have any questions for Jared, please do use the chat box and send it to us. And we will make sure that we'll forward all your questions to him and then document it after the webinar in a written form. So I'm going to now play his presentation.
Hello everyone, my name is Jared Hostetler and I am a licensed engineer in the US. I'm a volunteer with EWB USA and today I'll be providing a brief overview of water storage tanks in solar pumping schemes, particularly in the humanitarian context. People often ask about the suitability of batteries in solar pumping schemes and how they compare functionally to water storage tanks. And today we will discuss why water storage tanks are a vitally important component in solar pumping schemes and why tanks are generally a superior design alternative to batteries. Both batteries and water storage tanks are capable of storing energy. Batteries store electrical energy, while water storage tanks, when they're elevated, store potential energy as pressure that's then converted to kinetic energy when the water flows out of the tank and into the distribution system. And while batteries can be expensive and maintenance intensive and can greatly increase the complexity of a solar pumping scheme, water storage tanks, on the other hand, are widely available, they're relatively inexpensive, and they're simple to operate and maintain. Moreover, water storage tanks provide a number of functions within a solar pumping scheme. They allow for periods of instantaneous demand throughout the day that exceed the instantaneous supply. They provide emergency water storage if the pump is unable to function due to mechanical or electrical failures, or if there's low irradiation. As we've talked about, when they're elevated, tanks provide head pressure to the distribution system downstream. And then they also provide contact time and mixing volume for any chemicals that are used to disinfect the water, and that's typically chlorine. So here's an example. This photo was taken at a refugee camp in Uganda, where 3 10,000 liter HDPE tanks were elevated on a 10-meter steel tower, and this provided sufficient storage volume and also head pressure to the distribution system, which consisted of buried piping and tap stands. When we talk about sizing water storage tanks, this really is an exercise in risk management. So more storage volume is going to equal less risk, but that's going to come at a higher initial capital cost, while less storage volume is more risky, but comes at a lower initial capital cost. And that balance is something that the designer needs to strike. I wanted to go over some design guidelines from the literature regarding water storage tank sizing. And this first example comes from the 10 state standards, which is widely used in the US where I'm located. And essentially what this guideline states is that at a minimum, 1 day of average daily demand should be provided in terms of water storage. At a maximum, 5 days of storage should be provided. And that's due to water quality concerns in the distribution system if the water sits for 5 days. There's some additional flexibility also mentioned when standby power is provided, something like a diesel generator. This next example comes from the Field Guide to Environmental Engineering for Development Workers, and I'm not going to read the full table, but I did want to highlight one row in particular, and that's the second row here, where water supplied is equal to or slightly exceeds the demand in the system. That's typical for many solar pumping schemes, and in that case, 50% of the maximum daily demand is the minimum storage volume that's required, or at least recommended from this resource. Now, how maximum daily demand is calculated and determined varies often by local regulations, but I think this is a helpful table. The Kenya Ministry of Water and Irrigation Practice Manual references a recommended storage volume that is equal to 50% of the daily system demand. It also references a mass diagram that's used to calculate the storage volume where water is pumped for less than 24 hours per day. And this is applicable for all solar pumping schemes where we're pumping typically 6 to 9 hours per day when there's sufficient irradiance. So under these circumstances, a mass diagram would need to be developed and used for water storage tank sizing. The Uganda Ministry of Water and the Environment's Water Supply Design Manual provides an example of this mass diagram. Here, supply is presumed to be constant and is plotted as a line. Likewise, cumulative demand throughout the day is also plotted, and the maximum difference between these lines is then equal to the minimum storage volume that's required. I want to note that in most solar pumping schemes, water supply is not constant. It varies with irradiance. So using this methodology can be challenging when sizing water storage tanks. Now I want to step through a brief design example where we will look at hourly supply and demand in order to optimize the design of the water storage volume provided. In this example, we'll look at a community with a population of 2,500 people. The average per capita demand is 20 liters per person per day, and so therefore the average daily demand in this community is 50 cubic meters per day. We have a borehole with a safe yield of 9 cubic meters per hour. We want to set the design pumping rate at approximately 80% of the safe yield of the borehole so that we don't over pump. And so therefore the design pumping rate is 7.2 cubic meters per hour. The head condition for the system is approximately 124 meters. And we'll be looking at the minimum month irradiation, which in this case is 4.9 kilowatt hours per meter squared per day. Next, we will look at the daily irradiance profile in the minimum irradiation month, and we will size the array to optimize water production per installed solar power. So basically, at what array size do we get the maximum cubic meters of water per kilowatt installed solar power? And then we'll use that motor power versus flow relationship that we developed previously to inform us how much water is produced in each hour of the day. Finally, we will plot the diurnal demand, and that's represented here in this green curve, where we have demand increasing and peaking in the morning and then peaking again in the evening. We'll plot that against the water production throughout the day, and we'll compare the hourly supply to the hourly demand. Of course, this is in the worst month based on the irradiance data that we used. And we'll determine the storage volume that's required to balance these flows on a daily basis and determine the additional storage volume desired for emergencies. So in this case, if we start with a volume of 20 cubic meters or 20,000 liters, then we get to a point in the middle of the day when our tank is empty. However, if we start with 25 cubic meters of water, then yes, there's a significant dip, but as we begin to produce water, the water level in the tank or the volume that's stored comes back up. So in this case, we could say that 25 cubic meters of storage ensures that water is available even in the minimum month irradiation condition. And again, the design demand for this example is 50 cubic meters per day. So in this case, we would say 50% of the average daily demand is an adequate storage volume to protect the needs of the system and to provide the water that's required for this community. We have discussed a variety of guidelines, recommendations, and methodologies for sizing water storage tanks and solar pumping schemes, and I wanted to provide a summary statement, and that is that an hourly supply and demand analysis, which is the example that we've just stepped through, this is the most precise method of sizing water storage volume requirements for a solar pumping scheme. It does enable the designer to optimize the storage volume specific to the water system. However, this method requires detailed knowledge of the piping system, the pump, the solar panels, the motor, and the inverter or controller that's proposed, as well as local irradiance and temperature conditions. And then possibly the most challenging thing to ascertain is the hourly diurnal demand, and that can be really difficult to determine in some of the remote communities where we're looking at implementing solar pumping. A good general rule on more of a daily basis rather than an hourly basis is to provide a storage volume that's equal to the daily demand. Where this isn't feasible due to space constraints or capital costs, if that's cost prohibitive for the system in question, a minimum storage volume of 50% of the daily demand may be sufficient, but should be verified with a detailed hourly analysis. There are a number of challenges with water storage tanks in solar pumping schemes when they're not appropriately sized or configured. So an undersized storage tank won't provide enough storage volume to meet peak demands or potentially meet emergency situations. And so the graph on the left shows an example where if 20 cubic meters of storage were provided, that tank would bottom out, and there wouldn't be quite the volume required in the middle of the day. Where if we simply increase that volume to 25 cubic meters in this example, we'd have sufficient volume throughout the day to meet those peak demands. Oversized water storage tanks also provide some challenges, and namely can result in significant water age and then subsequent deterioration of water quality. So the disinfectant residual might be reduced with increased water age, especially at high temperatures, and then you have regrowth of microbes and other issues with the water quality. And then if the water storage tanks are not sufficiently elevated relative to the downstream distribution system, you won't have sufficient head, and you might get into situations where there's not sufficient pressure at all the tap stands in the distribution system. I want to touch briefly on disinfection in solar pumping schemes and how that pertains to our discussion today. And the big challenge for disinfection in a solar pumping scheme is that flow is variable. Flow is going to be a function of input power. And so the figures here show a daily irradiance profile at a specific location. That's the figure on the left. And then on the right, that figure shows anticipated water production of a solar pumping scheme at this location. So you'll see that as irradiance increases throughout the day and peaks around noon, so does flow. So flow, of course, is a function of input power. And we don't always design these systems that way. We might design a system looking at more of a daily profile than an hourly one. But in reality, flow is a function of input power. And so that can provide some real challenges when we're looking at disinfecting that water at a variable flow rate. But of course, every challenge has a solution, right? Or a number of solutions. And as far as disinfection in a solar pumping scheme, there are a number of solutions. And we're going to talk first about tablet chlorination. So tablet chlorinators are shown in these figures below, and they're a neat way of disinfecting, especially low turbidity groundwater. There's no moving parts. Flowing water erodes the tablets, which are typically calcium hypochlorite, and this results in a free chlorine concentration in the finished water downstream. The dose can be controlled if a portion of the flow is bypassed, and that helps to adjust that free chlorine concentration. Flow limitations may require multiple parallel tablet chlorinators, and so that's seen in this photo here on the left. This is an installation in a refugee camp in Uganda, and this specific installation is fed by a high-yield borehole, and so multiple parallel tablet chlorinators were required here. And then also tablet chlorinators are generally limited to low head operating conditions, so they want to be, we want to locate these as close to tanks as possible. The photo on the right here is from a municipal installation in Puerto Rico, and the chlorinated water actually discharges immediately down into the storage tank below, so that the pressure at that chlorinator is minimal. Flow activated chemical dosing systems are another means of disinfecting, again, especially low turbidity groundwater in a solar pumping scheme. And so here, it's flow-paced dosing of a liquid hypochlorite solution. Again, no external power is required. The velocity of the incoming water drives an internal piston in this unit, which draws the hypochlorite solution up into a blending chamber. These operate at a wide range of flows and pressures. Of course, the liquid hypochlorite solution would need to be made up prior to use. So often that's made up every day or every few days. There's an upstream screen on many of these units that needs to be regularly purged to remove particulate matter that's trapped. And then There can be issues with internal corrosion, which may require frequent replacement of wear parts, especially if there's a strong hypochlorite solution that's being dosed. So this photo is from an installation at a refugee camp in Tanzania, and you can see the black tank at the bottom where the liquid hypochlorite solution is stored and then is pulled up into the blending chamber and dosed into that stream of water with those blue pipes that side stream off of the main line. And finally, we'll talk about chemical metering pumps, and these provide precise flow pace dosing of liquid hypochlorite solution or other chemicals that you're trying to dose. They can be integrated with a flow meter, whether that's via a pulse signal or a 4 to 20 milliamp signal. There's lots of options. These operate at a wide range of flows and pressures. As before, a liquid hypochlorite solution would need to be made up prior to use, and an external power source would be required, which can present some real challenges in a remote environment, which is often the case where we're looking at solar pumping. So where you don't have alternating current power available, you might need to look at something like a solar powered a power pack, which would be equipped with lithium ion batteries to provide a consistent source of power. This is the one application where I would really recommend looking at batteries. Otherwise, as we've discussed, there's a lot of limitations and operational complexities when we look at integrating batteries into a solar pumping scheme, but a small power pack basically to provide just the power required for a metering pump. That's one application where I think batteries make some sense if you want to look at chemical metering pumps for disinfection. This photo specifically is from an installation at a refugee camp in Tanzania. The hypochlorite solution is prepared daily in the pink bucket at the bottom of the photo. And this specific pump, at least at this time, was powered by a diesel generator. So you'll see the electrical plug kind of over on the right side of the photo. Again, we would probably look at a different option long-term for a solar pumping scheme where we don't want to be operating a diesel generator for an extended period of time. I hope this discussion has been helpful to you. If you have questions, please do not hesitate to email me. I've got my email address here on this slide, and I look forward to chatting with you about solar pumping schemes. Thanks for your time today. Bye-bye.
Thank you. After that presentation, I'm back to my screen. And before we go to the polls, I just want to quickly reiterate, if you have questions for Jared's presentation, and although he couldn't join us in person today, please do send them to us via the question box. And what we will do is we'll compile all of them and forward it to him, and then later document it in a written form so that you can access them afterwards, after the webinar has ended. And we will share the link of the recording, the presentation, and as well as a written question and answers in a follow-up email with you. So as you can see in the screen, it's time for some poll questions. So I'm going to quickly launch a poll question on your screen. And please do tell me, where are you logging today from? It seems like, yeah, the poll questions is now online. And these questions are to understand you, the audience, better so that we can plan the upcoming webinars according to your time zones and other practical needs. So I have the answers coming in. I'm going to leave it for another 10 more seconds. So maybe another 5 more seconds as people are still answering the questions. So now I'll close the poll and display the results. So today we have most of our attendees coming from Africa, followed by Asia, Europe, and others. So welcome to all of you one more time. And now I'm going to pull up a second poll question. So please do tell me in which sector do you work, whether it's humanitarian sector, development organization, humanitarian and development, academic research, and so on. So I'm going to leave it for another 10 more seconds as the answers come in. Maybe another 5 more seconds as we have the answers coming in. And now I'm going to close the poll and display the results. So today we have our audience who are mostly working in the humanitarian and development organization and only purely humanitarian organizations, and followed by academic and development, and also a significant portion working in other sectors. So thank you for taking part in the poll question. And now we are back to our presentation, and I would like to now invite our second presenter for today, Brian Maxoli. Brian is a water and sanitation advisor in Oxfam's global humanitarian team and has over 30 years of professional engineering and management experience. And today, Brian is going to present a case study from Bangladesh. Brian, I'm going to send you a request to share your screen. So please accept my request and share your screen.
So hopefully you can see my screen and you can also hear me.
Yes, loud and clear. Please proceed.
Great. Hi everyone. For the next 20 minutes, I'm going to talk about a review I was part of in KUTAPALONG in Bangladesh at the end of 2019. What's interesting about KUTAPALONG, you might ask? Well, it's the biggest refugee camp in the world. It hosts over 700,000 people. And in 2018, a water master plan for the camp was developed based on meeting everyone's water needs through solar pumping. So to my knowledge, in the humanitarian sector, implementing solar water schemes at such a scale has never previously been done before. There's 3 parts to the presentation. I'm going to start by giving a background on COX'S BAZAR, which is a very interesting context in itself. I'll give an overview of the water networks and highlight some of the factors affecting the performance of solar systems. So this will touch upon water storage, shading, seasonality, and decision-making or human interference. And I'll conclude by giving my own reflections and the learning that I took away, which hopefully will also be relevant for the context where you're working. For those who are not familiar with the background of this crisis, in 2017, there was a mass movement of Rohingya people fleeing violence and persecution in Myanmar. And it's estimated up to 1 million people fled to Bangladesh, and most settled in Cox's Bazar district. People self-settled on hillsides, building temporary shelters, and in the space of a few months, thousands of tube wells were sunk and tens of thousands of latrines, often just a few meters apart, were dug. With time, the camp has steadily developed to the point where it's more similar to a semi-permanent urban settlement or city, more than a temporary refugee camp. KUTAPALONG, which is often referred to as the mega camp, is the largest camp in Cox's Bazar. It's spread over an area of about 50 square kilometers. And in anticipation that its 700,000 inhabitants were likely to be there for the long term, and with concerns about the groundwater quality and latrines contaminating shallow wells, the wash sector developed a master plan to provide chlorinated piped water throughout the camp. And after considering different options, the master plan was designed around a decentralized system of multiple solar powered water networks. So this divided the camp up into over 100 distinct zones based on topography, and it was envisaged that each zone or each catchment would be supplied through a single borehole, a solar pumping system, water storage tank, and then a simple branch network. Final bit of background, this map shows the average daily solar irradiation across Bangladesh. COX'S BAZAR is located in the far south of the country where the most favourable solar conditions are. There is, however, the annual monsoon season, so extended periods of cloud cover, particularly during June, July and August. And there's always been a concern or a question mark as to whether solar pumping systems could reliably meet demand during this time. So as you can see on the graph, there's a noticeable reduction in irradiation during the monsoon months. Onto the study. At the time we carried it out, over 30 solar schemes were operating, with many others under construction. We were hired by UNHCR, so myself and one other colleague hired by UNHCR, so we focused on 17 systems completed in the section of KUTAPALONG camp that UNHCR managed. So they wanted to understand better the performance, particularly because monitoring reports being collected and submitted by different agencies were giving quite variable feedback. This photograph that you can see here is fairly typical because the camp is so densely populated. In some sites, there's no option apart from building on top of people. So these solar panels, they've had to be elevated 3 to 5 meters high, and the roofs immediately below people's dwellings. We started by uploading data stored in each pump controller via Bluetooth using a mobile phone app called Pump Scanner, developed for Lorentz pumps. And we were able to see on a daily basis, hour by hour, how much water was pumped from the date of installation. So this varied from 3 to 9 months of data. We then visited sites to undertake a technical appraisal, site inspection, interview operators to understand factors which may affect the performance. And finally, we carried out focus group discussions with refugees to better understand habits around water usage and satisfaction levels. Onto the findings. There's an awful lot of data on this slide, which I don't have time to go through. The main point I'd like to focus on is in the red box, which is essentially the actual production from each pump compared with the expected design output, so based on the manufacturer's software and sizing tool. As you can see, in the majority of cases, the actual output or production of water was much less than might be expected. On average, this was 54% of the design potential. And there was only one site where actual output exceeded the expectation, and one other site that was close, and I've highlighted these in yellow. The next thing we started looking at was reliability. So how many days in the year people are getting sufficient water, and we used different benchmarks. Severe minimum target is 15 litres per person. UNHCR standard for protracted crisis, 20 litres per person per day. And we took 10 litres per person as a minimum acceptable target. The best performing network was Camp 4 Extension, which I'm proud to say was being managed by Oxfam at that time, where so 93% of the time people were able to access 20 litres or more, so for 11 out of 12 months of the year. On the other hand, there were several systems that only supplied an average of 10 litres or below, which explained why UNHCR was getting conflicting information about the performance of the solar pumping systems. The figures were surprising, but not necessarily a problem. We already knew that in sections of the camp with high density of tube wells and hand pumps, people continued to use them because they were often the closest, most convenient water source. But this alone didn't fully explain some of the differences, which I'll go on to highlight now. We visited all 17 different networks, but I'll focus on the best and worst performing. This one, Camp 4 Extension, it's in the newer part of the camp. It's less congested than some other areas. Population is a little over 3,000 people. And there's also very few hand pumps in this area. So we knew that people did rely heavily on solar. There's plenty of storage here in relation to the population size. So this 95 cubic meter tank provides more than one full day's storage capacity. Tap stands are relatively plentiful and accessible with little or no queuing at water points, and therefore there's no supply constraints. People could easily take as much water as they wanted at any point of the day. To get a better understanding of the behavior of this system, we put a data logger into the storage tank for a few days, and this graph shows the daily water balance between supply, demand, and storage. So the blue line shows around 50 cubic meters of storage is in the tank at the start of the day, and you can see from around 5 a.m. people start collecting water. So that's the green bar on the graph. Because the pump is not working at that time, the level in the tank reduces. But then from a few minutes before 7 a.m., the red bar in the graph, the pump starts, and by 7 to 8 a.m., production is greater than consumption, so the tank starts refilling again. And you can see for the next 4 hours, so these red bars, the pump output is fairly constant, suggesting it's performing at or near its maximum design output. And this continues until midday when the tank is full, so the pump automatically switches off. And this is the important bit. For the next 3.5 hours, which is the best solar conditions of the day, the pump is off until the water level in the tank starts dropping, and at 3:50 in the afternoon, the pump automatically switches itself on again. So what does this tell us? On this particular day, the solar pump doesn't need to work to its full capacity to meet demand. But if demand was to increase in future, the system can cope. Or if the solar conditions were much less favorable, for example, during the monsoon season, this spare capacity will then be needed. So in this system, it's all good. There's plenty of water in the system. There's no need for rationing. Tap stands are open 24/7. People are getting plenty of water. I'd now like to show the same data for one of the systems where people are only getting 10 litres of water per person. So I'd first like to explain the lower graph, which shows the results of a household survey of when people collect water. As you can see, the most popular time is early morning and evening. And the problem we found was that for many of the solar networks, tap stand opening hours are 7 a.m. to 7 p.m. So people who want water before or after that, which they do because that's the coolest time of the day, they're forced to use the hand pumps, which is the red bar on this graph is people taking water from hand pumps. The orange bar is tap stands associated with the solar systems. So already 35% of water users have already taken water from hand pumps. Now look at the top graph. So you can see overnight there's around 60 cubic meters of water available in storage and available for the next morning, but people can't access it because the tap stands are closed. On this day, it's around 6:30, the tap stand's open, people start drawing water, but the tank level reduces slightly. By 7 a.m. the pump starts. Production is greater than demand, so the tank, the orange line, starts rising until 10 a.m. when the tank is full. And then we have a period of 5 hours, which is the peak sunshine, when the pump is actually working very little. Now, in this network, people are receiving an average of only 10 litres of water. The logbook was showing that the pump starts at 7 a.m. and stops at 4 p.m. But this was actually only half the story. So almost certainly this pump could provide double its current output. And this was where it became more interesting. We were told that tap stand opening hours were restricted because water needed to be rationed. But in actual fact, restricting the opening hours was the cause of the reduced water, creating a vicious cycle and a false perception that the solar systems are not performing and not able to produce enough water. So the problem here, which was also repeated at other sites, was due to a lack of understanding of the dynamics of a solar pumping system and this relationship between inflow and outflow, so supply and demand, and the importance of storage in balancing these differences. And the worst example we saw was an operator who didn't open the gate valve on the distribution line to tap stands until the tank was full. Moving on, shading is a major problem in COX'S BAZAR, and we observed that 50% of the solar arrays are affected by shading to some extent. Most of the camp is densely populated, and parts of the camp there's dense vegetation. So there are restrictions on where solar arrays can be put, and it is difficult to get permission from the host community to remove or trim branches on trees. But some problems are totally avoidable. For example, you can see here building a 3.5 meter tall pump house which casts a shadow across panels immediately adjacent. This was observed on multiple occasions. As this graph shows, the relationship between shading and power loss is non-linear, i.e. a small amount of shading causes a disproportionate loss of power. And this wasn't fully appreciated by engineers in the field. These photos are taken using a sun tracker app, which shows the path of the sun at different times of the day and different seasons. As you can see, the PV array on the left is being shaded by an adjacent water tank, which could have been easily avoided. At the same site, the panels were casting shade on each other. So there's 3 strings in parallel, and the top row of one string was casting shadow over the bottom of the other at certain points of the day. The other 2 photos, really perhaps these trees need to be totally chopped down, but it's something that should have been considered at the planning stage. Half of the networks had the option to be connected to a backup diesel generator in the event that solar pumping is insufficient to meet demand. What we found was that in the majority of cases, these were not being used. The above graph is an interesting comparison between a standalone solar system and a dual power hybrid pumping system for 2 different months. So the blue bar is the dual power system. So where it shows a solid blue bar, it's when solar is operating. Where it's white, that pump is being powered by generator, and the yellow is solar only. So during a sunny month in October, which is the top graph, both systems operate off solar only, and the performance is almost identical. However, in July, you can see the lower graph, which is the monsoon season, the performance of the 2 networks deviates significantly. But it's the solar only network without a backup generator that performs much better. So these results were, yes, it's counterintuitive. You would expect the solar equipped borehole with a backup generator to produce more water during cloudy days, but the reality we found here was the opposite. Now the full reason, it's a bit more complicated. There's slightly different specifications to the pumps, and I don't have all the information, but the figures don't lie, and ultimately what's important is that people are accessing water. So when the generator is run, it's not run for long enough periods to compensate for the reduced production from the solar. And this is common with dual power systems. They don't necessarily increase reliability as expected due to the complexity of operation. So I'm not saying that in all cases backup generators are unnecessary, but what we found in KUTAPALONG is that the investment was not justified. Performance, sorry, performance during the monsoon. So the caveat here is for well-managed systems with good storage capacity, PVs not in the shade, and pumping running in auto mode without unnecessary human interference, then solar performance during the monsoon is satisfactory. The upper graph shows two solar systems, and there's only 3 days in the month when there's less than 10 litres of water available per person. The vast majority of days people are able to access 15 litres or more, and anecdotal evidence from focus group discussions confirmed that this was acceptable. One important point to highlight here is days marked with an F indicate the storage tank filled up, and on that day, so storage tank filled up on that day and the pump turned off. So more water would have been available those days if demand had been higher. This graph is interesting to illustrate the point about human interference. At this site, for 1 month, the Oxfam engineer, he couldn't understand why production was so variable, even though the weather was very settled. He asked the operator, checked the logbook, couldn't explain it. It was only when he looked at the pump scanner app, which showed the actual running hours, that he figured out what the problem might be. And on 19th of April, the operators were instructed to never touch any of the controls, either the valves or the on-off switch on the pump. And from that point on, there's a dramatic improvement in the running hours that's evident from this graph. So the operators were acting in good faith, but they were unaware that their actions were actually detrimentally affecting the overall performance of the network due to a combination of sometimes closing the tank outlet gate valve, turning off the pump overnight or when it was cloudy. And an operator doesn't need to make these judgments. So conclusions, this presentation, I've deliberately highlighted some of the challenges we found, but generally the performance of the completed solar networks was good, but it is fair to say that they're not yet reaching their potential. As a headline though, what amazed me, and one of the reasons I wanted to share this case study, is the ambition of the water master plan in COX'S BAZAR. To have a water supply for a refugee camp of 700,000 people, which is effectively a small city, supplied through solar pumping, I think is absolutely incredible. 10 years ago, I worked in the Dadaab refugee camp in Kenya, which at the time was also the world's biggest refugee camp. But it was only in 2012 that Oxfam installed the first solar pump there. So in less than a decade to progress from that to this is amazing. I should stress that only 30 out of the planned 100+ solar networks have been completed at the time of our study. So currently solar isn't yet the main source of supply across the camp. It probably won't ever be the sole supply of water because there are so many shallow wells and hand pumps, but it is on course to become the primary means of supplying water if the master plan continues to be rolled out. What I took away more generally was to reflect on other solar water schemes that I've been involved with over the last 15 years of my career and wonder how many of them are not performing to their full potential. And if I'm honest, I couldn't tell you. So I'm not suggesting you should be putting data loggers in every water tank, but there are many different ways to easily check performance and understand the linkage between different components of a solar system and the consequences. So it's not just about one element, the pump, the solar array, water storage, the number and location of tap stands, all are important. But it's also not about the perfect design. Of equal or more importance is understanding community behavior and habits, and then how systems are managed to meet these needs. So the final slide I showed highlighting the impact of an operator flicking a switch or closing a valve. It's a small thing, but the impact might be thousands of litres of water per day, and the difference between queuing or no queuing at tap stands, rationing or no rationing. So hopefully some food for thought. I'll stop there to allow some time for questions. I think I'm over time, so apologies for that. I'm aware I might have rushed through some bits, but hopefully it wasn't too confusing. Ranisha, back to you.
Thank you so much, Brian. I'll first maybe quickly switch back to my screen. So thank you for the amazing presentations. I'm pretty sure we all learned a lot. And if you have questions for Brian, please use the chat box on the right side of your screen and just type in your questions, and then we will address all of them to Brian during the Q&A round towards the end. So moving forward, let's have one more poll. So I'm going to drop a new poll question on your screen. And as I mentioned before, this webinar is actually part of an ongoing webinar series where we already organized 2 of the other webinars. So please do tell us if this is your first time joining the SPWS webinar series, or you have already joined one of our other webinars. So let's leave it for another 10 seconds so that our audience, all of them, can answer. And now I'll close the poll in about 5 more seconds and then display the results. So most of our audience said that this is the first time attending the webinars in the SPWS webinar series. So my colleague has already dropped a link to the past webinars in the chat box. So please do have a look at those links after this webinar ends, because it's part of a series, we have designed it in a way that the first one talks more about the pumps, the solarization of existing systems, and so on, so that it gives you, by the end of the series, you have a comprehensive overview about solar water pumping systems in the humanitarian settings. So now I'm gonna close the poll results and move back to our presentations for today. So moving forward, I would like to invite our third presenter for today, Antonio Torres. Antonio has worked in the WASH humanitarian sector and in progressively senior roles at IOM for nearly 12 years. And today he's going to share some of his experience about what are the practical considerations for planning solar water pumping systems in humanitarian setting. Antonio, I'm going to send you a request to share your screen. So if you could accept my request and unmute yourself.
So, hello. Thank you, Ranisha.
Hi. Yes.
So, hello, everyone. Good morning, good afternoon, or good evening, depending on where you are. As mentioned in the short intro, my name is Antonio Torres, and I work for the International Organization for Migration as WASH advisor based in the IOM headquarters in Geneva. So I'm privileged to have been given the opportunity to share some of the experiences and lessons learned while implementing solar power systems for water supplies in emergencies. And for this presentation in particular, I will bring an example of my experience in South Sudan. So before I start with the example, I would like to present a small overview of WASH in IOM and why we have solar as a priority. So the International Organization for Migration is the leading intergovernmental organization in the field of migration. We support the migrants and our member states to ensure an orderly and humane management of migration. We work to address the WASH needs that are faced by migrants, including the displaced, since this contributes to respond to the mobility dimensions of migration crises. Our WASH interventions take place in response to emergencies, but also in transition and recovery situations, and we also have a role in emergency preparedness. So most of our WASH programs, the largest WASH programs, are implemented in countries affected by conflict and where the crises are protected. So the South Sudan, Sudan, Somalia, Nigeria, and Yemen, countries which are also impacted by recurrent natural disasters and disease outbreaks. So in this slide, there are some figures that could give you an indication of the scale of IOM WASH programs globally. So why solar? IOM WASH programs have been increasingly adopting sustainable energy technologies and approaches. Our focus has been in reducing dependency of fossil fuels in the energy generation for water supply. In that regard, nearly all of the water supply systems that IOM runs are solar powered. Yeah. And an example of that is that one of the largest solar water powered supply systems implemented in emergency humanitarian settings has been implemented by IOM in the Rohingya camp in Bangladesh. Also, another factor is that IOM leads the Global Solar and Water Initiative project, which is a project that has been active since 2016, mainstreaming the use of solar power for water supply through capacity building and technical support provided to WASH agencies globally. So now I will go through the example from South Sudan. And to put you into context, South Sudan is a country with a history of conflict, protracted displacement, overlapping hazards, and alarming WASH needs. The locations of displacement are usually in hard-to-reach areas where access is constrained due to poor road infrastructure, rainy season, and insecurity. During the rainy season, nearly 60% of the country is cut off. Materials and equipment usually need to be airlifted, and sometimes only a helicopter can reach. There are serious security risks for humanitarian staff and humanitarian assets. Materials and specialized equipment for the implementation of WASH activities are mostly unavailable in country, and the procurement takes an average of 3 months. Local private companies that could implement WASH activities, such as the drilling of boreholes and the installation of water supply systems, are generally poorly equipped and technically challenged. So, what are the main reasons, from my perspective, for implementing solar systems in South Sudan? First one is the solar energy potential. Are favorable conditions for solar water pumping given the location of the country, in the solar belt and its climate, which allows high solar irradiation throughout the year. Another factor, another reason is that is reducing the risks related to the interruption in the supply of fuel. So our work in the country is in hard-to-reach locations, which means a total absence of the electricity grid, not a reliable supply of fuel and other consumables for generators, including spare parts. So when conflict was at its peak, all supply lines were closed for several weeks. And all this in addition to the frequent theft and mismanagement of fuel. The other reason is reducing operational costs. So given the hard-to-reach location in which we work, the cost of fuel was very high since it had to be transported by air. For instance, the cost of fuel between 2014 and 2018 fluctuated between $1.2 to $3 per liter of diesel. And given challenges to mobilize drilling equipment, authorizations for drilling of additional boreholes, and an increase of displaced populations in the camps, the best alternative to ensure a sufficient and constant supply of water was to implement a hybrid solution of power, merging solar and fuel generators in our water supply systems, instead of going for strictly solar systems, which will have been the ideal scenario in terms of cost efficiency. So by having these hybrid systems, the pumping could be extended to night hours, and the deficit in water supply in the camps was shortened. Through these systems, we recorded reduction in operational costs between 49 to 58% when we compare our hybrid systems with traditional standalone diesel generator powered systems. The other reason is the good return of investment. So given the high operational cost for diesel generator power systems, the break-even point for our IOM hybrid systems was between 1.2 to 1.4 years, which is relatively low. Yeah? The Global Solar and Water Initiative project on its visit to South Sudan in 2007 calculated an average break-even point of 2 years for the country. So in this slide, you can see an example of a cost analysis for one system in South Sudan made by the Global Solar Water Initiative project for a standalone solar system. And as you can see, the break-even point is of 0.7 years, which is indeed a very good return of investment. And finally, environmental sustainability, which is a very good reason on its own, which apart from reducing carbon emissions, it contributed to prevent environmental pollution linked to the use of fuel and other consumables for generators, which generate waste and could pollute soil and water sources. So I will go through with some of the barriers that we face in South Sudan to implement solar systems. In-house technical knowledge. I think this is perhaps the most important barrier to overcome. So if there is no basic technical knowledge in terms of the design and implementation from WASH staff from within the organization, it won't be possible to guide the design of fit-for-purpose systems, supervise construction companies, guarantee the quality of their work, and the quality and appropriateness of materials and equipment. Another barrier was the emergency funding schemes, no? So funding for emergencies is normally for the short term and mostly for 3 months or 6 months interventions. And in South Sudan, although being a protracted crisis, this was the case. So with this scenario, it was usually difficult to include solar power systems in funding schemes at the onset of emergencies, given the larger capital investment compared to diesel generator systems, the limited funding available for the whole response, and the other WASH needs that needed to be met, which usually are underfunded. Another reason is the or barrier is the lack of knowledge of the groundwater resource and its potential. So in South Sudan, the knowledge of the groundwater resource was limited, which hindered the capacity to provide quality data for sustainable designs. There was little investment in studies on the groundwater resource. The databases were not well maintained, so the information available was either all or mostly anecdotal, and WASH actors were failing in properly monitoring and recording the performance of constructed boreholes to assess changes in water levels and water quality. And in addition to that, the pumping tests were often done incorrectly, and is data badly analyzed, leading to unsuitable designs and poorly functional solar systems. The other barrier identified as the lack of capacity of the local private sector. So the performance of the local private sector was not consistent, and most companies were ill-equipped to do the job. So there was a general mistrust in their capacities, and companies based in neighboring countries were preferred. So hindering the capacity development of local resources, which generated issues such as delayed responses, costly implementation, and lack of materials and spare parts in the country. And finally, the prejudice and misconceptions around solar. That solar systems are too costly, which is not necessarily true given the good return of investment for the context, that is too technically complex, that the systems are unreliable during cloudy days, and that is too risky given insecurity. So how to overcome these barriers? Training internal capacity building. So investment in capacity building for staff within the organization is a must. And not only on the technical components of the solar installation, but also in the analysis and interpretation of hydraulic parameters, like data from pump testing, and also, which is very important, in the economic analysis to be able to calculate the return on investment and other economic indicators that could inform the economic feasibility of the solar systems and assure donors of the value of money of their investment. Establishing groundwater monitoring programs. So a good knowledge of the groundwater resource before the end of the borehole through hydrogeological assessments, whether using geophysical methods, direct observation through analysis of nearby groundwater sources, desk studies, or even using remote sensing data, or the combination of all, is key for a successful drilling. And a successful borehole is key for a successful solar system. So, and anyhow, that's not all. A good interpretation of pumping test data once the borehole has been drilled, and the analysis of the effects of the long-term abstraction of the groundwater, meaning understanding the groundwater potential, is also key for appropriateness of solar designs. And this is of special relevance when the water demand is high in overpopulated camps such as South Sudan. In such case, maintaining a rigorous monitoring program of extraction rates, water quality parameters, and water levels allows a better decision-making to inform new systems or expansion in case of additional population influx to the camps, which was very often in South Sudan. So this is like you can see a 3D geological model of the subsurface of a displacement camp in South Sudan, which was part of a hydrogeological assessment that was commissioned by IOM in order to inform the drilling of additional boreholes. So in an area of less than 1.5 square kilometers, more than 150,000 people were facing shortages of water despite having 12 boreholes drilled. And those boreholes were not productive because they were drilled in a rush of an emergency without a sound understanding of the groundwater resource, were not tapping rightly into the aquifer. Another way to overcome the problem through meaningful collaboration and reciprocal learning with the local private sector. So I think it's important to give the opportunity of work to local companies and working in a collaborative approach. So as an example, breaking the working components that the local companies could deliver while allowing international companies to work on the components for which it is known that the local private sector has weaknesses, allowing them to work together so the local sector could be benefited in knowledge from this collaboration. Similarly, having well-trained staff that can supervise contractors and simultaneously improve their capacity to on-the-job knowledge transfer. And finally, increasing the awareness on solar energy, promoting the increased knowledge about solar water pumping among all stakeholders, including the government, the beneficiaries, and the host communities. So we can start to disentangle some of the misconceptions around solar that represent a barrier for its optimal adoption. And also promoting an increased awareness to donors and actors within the humanitarian community with the right evidence of the financial viability and value for money in funding solar water supply systems during emergencies. So making sure that the solar systems work well in a harsh weather and insecurity conditions was challenging. Solar panels need to be cleaned regularly, especially in dusty environments such as South Sudan. Anyhow, unfortunately, provisions in the design for easy cleaning are not considered from the beginning and frequently are introduced when the panels are already installed. To deter theft and vandalism of solar systems, it was crucial empowering the displaced community to take ownership and accountability of the services and infrastructure provided in the camps. This was also crucial to ensure good governance of the systems and long-term sustainability. The creation of community-led water management committees, even before the systems were in place, was essential to assure conflict mitigation and an equitable access to water. In the same line, the knowledge for the operation and maintenance of these systems needs to be entrenched within the community members. The operators of these systems need to be members of the community. These structures also help in the monitoring of the system. And during lockdowns due to insecurity, which were several, where staff was not able to access the systems for weeks, they were able to run the solar systems and ensure water to their communities. And last one, ensuring a reliable and efficient monitoring of the systems using wireless data collection devices that were installed to gather real-time data on pump performance, extraction rates, and water levels. So I would like to wrap up my presentation, providing some recommendations from my experience. So in situations of displacement and during the emergency phase, I will recommend planning for hybrid solar water systems, since provide backup capacity to address fluctuations of population, bad weather, and breakdowns. Also, as long as it is economically viable and without undermining funding for other components for the response in emergencies, I will recommend the implementation of solar water supply systems from the onset, taking a no-regret approach, since humanitarian emergencies are likely to become protracted. Anyhow. I think that there is a need to pay more attention to the monitoring of the performance of the systems and being more accountable with the aquifers and prevent over-extraction and encourage a rational use of water from solar systems. And as the final takeaway, I would like to stress again the need to invest and make efforts in capacity building and gain more knowledge on the technical aspects, including the economic analysis. And this should not be only for the staff inside inside the organization, but also to the operators and other community members that might be involved in the operation and maintenance. And when possible, including the strategies that allow targeting the local private sector. So this is all. Thank you very much. I hope you find this interesting and informative. Thank you.
Thank you so much, Antonio. Definitely, it was very enriching and informative. So I will now switch back to my screen first of all. And now we are in time for our Q&A round. And we have been receiving a lot of questions. So maybe without further delay, I will quickly jump to the questions. And the first question is for you, Brian. In one of your slides, you talk about user behavior, and you showed us a graph where the water, like the pumping was in the afternoon, but the refugees who need the water, it was mostly during the mornings and evening time. So if you could just one more shed light on what would be an optimal options for this kind of situation, and also share other user behaviors that you know from your experience, but are mostly not taken into account, if you have any.
Okay. So I think the main point was that people like to fetch water very early in the morning, from 4:30, 5 o'clock, and then again late in the evening. So there was this disconnect between demand and how the systems were being run. So some of them were not opening till 7 a.m. in the morning, and it seemed to be partly a lack of coordination and understanding between how the systems were operating, that they weren't really responsive to people's needs. But then there was this additional issue that the operating hours of the tap stands were being limited because it was felt that there wasn't enough water, but because of the way they were being operated was having a knock-on effect with reducing the supply. I think more generally, as an engineer, we tend to focus on the designs and the technical hardware first, whereas perhaps that needs to be flipped and start with community engagement, understanding needs, and then designing based on that. So I'd say that's would be a general observation for any context, and it would differ from site to site.
Thank you so much. Antonio, if you have any examples on top of your head about any user behavior, please feel free to share.
Maybe I'll just jump in while Antonio is thinking again on. I think the other key thing in KUTAPALONG is people will tend to use the closest water point to them. So often that was a shallow well and hand pump. So access was prioritized more than quality. So the water from the solar system was chlorinated and for sure was safe, whereas that wasn't necessarily the issue with the hand pumps. So we could have, or agencies could have designed the solar systems with that in mind to ensure that tap stands were closer to people's dwellings.
Definitely, that's definitely a very one of the key points. Antonio, would you want to comment something? If not, I have another question for you.
Yes, I would like to comment regarding the user behaviors. I think I tried to stress one point in my presentation about the rational use of water, and I think that the point was directed into the behaviors of the community sometimes changes when they realize that that the system is solar and there is no fuel being utilized, and then it tends to incline people to waste water and to consume more than is needed, because there is no resources being spent on it, given it's solar. Practices that we have adopted to try to make sure that we have a clear understanding of what is needed, and to make sure that we tailor our interventions and that our designs are appropriate to the needs of the people are the water assessment surveys, water assessments or water consumption surveys that were implemented in camps, to try to make sure that that we can capture what are the requirements and the gaps as well. So the overall supply of water and the overall design was very informed, taking in account these surveys. These surveys also allow you to understand many other factors that are related in the access to water, not only because of the system, but also because of the structures that are working in it that are allowed proper management, such as the community structures that are working for the operation and maintenance and the water management committees. Yeah.
Thank you so much. I have one more question for you. It's I think you already addressed in your presentation, but to just reiterate it, especially when you are planning a system for emergency settlement, we don't have the prerequisite data like groundwater table or irradiance, and you might also not have feasible condition to do a feasibility study. From your experience, what could one do in such a situation?
Yeah, I tried to address that a little bit in the presentation. I think that you do the best that you can to try to gather all the information that is available, and to base your design on something. Yeah, whether it is looking at nearby boreholes and trying to look what are the water levels on water quality aspects that could provide some indications to your design. In the rush of emergencies, drilling of boreholes and designs of water systems are usually not guided by enough evidence, and that's what they fail. So I think that is important also to give time for that, and to consider that in the timelines that we are making for our drilling operations and our water supply systems. We need to ensure that at least there is some level of evidence gathering before we continue with operations. And I think it was very much evidence in South Sudan, in the example that I showed, with 12 boreholes that were not, I will say, not properly drilled, and then that even deterred donors and humanitarian community to fund additional boreholes, because they were not trusting in the capacity that the humanitarian community was having to provide good designs. So my overall recommendation in that is to take the time, make sure that hydrological surveys, some type of desk reviews, or looking at existing sources, sources of groundwater, existing boreholes, is analyzed, so you can base your interventions on some type of evidence. Otherwise, it will not work in the long term, and will face more negative consequences from these poorly or poor decisions, based on not good evidence.
And about the local irradiance, would it be looking at the World Solar Atlas or something like that?
The irradiance, yes. Well, I think using the software. There's the different software that can provide you some guidance for planning your solar design, and that's what is important also, to have in-house capacity, to from the onset of the inception of the solar designs, there is knowledge. We know where we are heading. So we have some tools, and with those tools, like the software that I'm mentioning, but also looking at the global solar map, and have clarity in these concepts. So the design can be guided in a better way. But definitely, I think that that the tools are there. We need is to make sure that those tools are used when appropriate and correctly, with the understanding of these tools, with the knowledge to understand these tools.
Definitely, thank you so much. Now back to you, Brian. I have a couple of questions for you. So the first one is, how was the number of taps per person determined in such a large camp? And then because the population density and terrain might have make it very difficult with queuing and all?
Yeah. I'll have to refer to my sphere standards. If I'm not wrong, it's general standard is 1 tap per 250 people, and I think that perhaps was applied in this context. But what we found in reality was that people in QUICKPOLL expected a higher level of service, and that was one of the contributory factors why they were continuing to use hand pumps rather than the high quality water for tap stands. So I think one of the recommendations of our report was for future solar designs have a greater ratio, so maybe 1 tap per 100 people instead of 250, and ensure that they are closer to people's dwellings than they were previously.
Thank you so much. And I also have a second question for you. Is there any effect on the distance between the borehole and the location of the solar panels in terms of energy losses?
There is, and I would defer that very technical question to one of the experts, Alberto or Asanath. So I think it's better they respond to that. So yeah, I think the point on that practically in relation to QUICKPOLL, there were limitations and restrictions on where you could put the array, and there is a trade-off. But if more thought had been given at the planning, it would have been possible to minimize the shade on some of those sites. I think let Alberto and Asanath respond.
Alberto, if you want to respond to that, please go ahead and unmute yourself and respond to that. Since I cannot get him online, so I will then maybe continue with the other questions. And we will try to get this answer to this question in a written form. So the other question is both to you and Antonio, is about if you have you had any experience where people were charged some amount of money for water, that's like a water kiosk, and if you have seen it being implemented in any of your experiences. Brian, maybe you go first with it.
In KUTAPALONG, there's no charge for the refugees for water. Water is provided free of charge. I think in other contexts there can be a charge for water. I'm familiar with water supplies for camps in Uganda, for example, where a certain allocation, a free allocation, is available to refugees, but host community who are using and benefiting from those same solar water systems are paying a small fee for access to water.
Thank you so much. Antonio?
Yes, I have been, I have some experience to tell about that, specifically in recovery and transition projects, where the solar systems are handed over to the community, and the community through the water management committee have some fees to keep some to make sure that they can maintain, do basic maintenance of the system, and generally those fees are, the design of those fees is accompanied by the humanitarian organization. In this case, IOM has done that in several countries, including South Sudan, and as I said, those fees are the idea is to get to affordable levels for those fees, and that this through the committee, the water management committee, that there is also transparency, and is known that these fees are going to be used strictly for making sure that everyone will have continued or sustained access to the water resource. So can be used to replace the taps, or to or to repair the drainage or the fencing in the water points. I think it has worked well in some cases, but also some cases there are I can relate some examples in which has to be or had to be reevaluated because it was not the most appropriate for the context, especially when you have recurrent cycles of crisis. Yeah, you think that the communities are stabilizing, but then you have another hazard coming on top, and then the people don't have access to livelihoods and makes difficult this kind of system. So I think that for this systems of trying to use some recovery or some fees, it needs to be well studied. It needs to be implemented right in the right phase of the crisis, no? Preferable during the recovery and transition, and it needs to be looked very well at the context and be able to have flexibility on those systems and give the community, the water management community, equip them with the knowledge and with some basic tools, for them to be able to run these systems with transparency, with good governance, at the end. That's.
Thank you so much, Antonio. And just for our audience, we also dealt with this topic in our previous webinar. And if you're interested to know more, also do check out our previous webinars. And that brings me towards the end of the webinar. And I see we have exceeded by 1 minute, so apologies for that. So a huge thank you to all our presenters for your amazing and enriching presentations. I'm pretty sure we all learned so much today, and that is also evident by the number of questions that have been coming in. And I know we didn't manage to answer all of your questions, but as promised, we will document them in a written form and send a link around so that you can access it after the webinar has ended. And there are also a couple of other resources that we do encourage you to check it out, like a copy of the ebook. And if you have any questions about the book or solar pumping in general, you can also contact Solar Hub at solarcurie@iom.in and other resources. So do have a look at that. And once again, thank you to all of you for staying with us till the end. And I wish all of you a good day. Thank you and bye-bye.
Thanks, Renisha.
Thank you. Bye-bye.